Welcome to The Explainer. Today, we are unpacking an absolutely fascinating, award-winning data analytics hackathon project by Sumit Saha, and it's called the Default Rate Semantic Engine. We're going to explore how this project brilliantly solves what is arguably one of the most universal, high-stakes data nightmares in the corporate world. I mean, if you've ever sat in a meeting where different departments brought entirely different numbers to answer the exact same question, well, you're going to want to pay close attention to this explainer. It's a real game changer.
It all starts with a question that, on the surface, sounds incredibly simple. How healthy is our loan portfolio? Imagine for a second you work at a major fintech company. You've got one real loan portfolio, right? With real borrowers and massive amounts of real money on the line. At the end of the month, the executive team asks this single, seemingly straightforward question to figure out the default rate. You would naturally expect one answer, but instead, asking this simple question results in absolute chaos. Let's look at what actually happens.
Okay, let's dive into this because this is where the mystery really deepens. The risk team comes back reporting a default rate of 49%. The finance team, they report 21%. The board's report shows a frankly terrifying 72%. And the regulatory team, they file a very neat, very tidy 0%. Now, keep in mind, this isn't some hypothetical academic exercise. This is the actual reality inside massive financial institutions worldwide. Think about the implications. The board is panicking, pushing for emergency reserves based on that 72%. Finance is telling the CFO that only 21% is at risk, suggesting a totally different provisioning strategy. Meanwhile, regulatory is technically compliant but offering absolutely zero insight into the actual portfolio health. Same portfolio, same loans, same date. 4 drastically different numbers.
Section 1. The problem with words, defining default.
So the reality behind those 4 drastically different numbers is fascinating. Everyone is right. Actually, the problem isn't the math at all. The problem is the word default. You see, the risk team needs an early warning system, so they count a loan as defaulted at just 30 days past due, looking only at the principal. To them, 49% of loans show early distress. The finance team, they only care about the actual hit to the profit and loss statement, so they use a 90-day threshold and deduct whatever they've already recovered, which lands them at 21%. The board operates under this strictly conservative policy, where any loan that has ever been restructured, even if it's perfectly performing right now, is forever flagged as a default. That skyrockets their number to 72%. And regulatory, they just need a specific 0% cohort filter for a highly specific government form. No cohort specified? The system naturally returns 0. They are all just using the exact same label to answer completely different business questions based on what they need. But here's the kicker. Before you can even begin to reconcile those definitions, you have to confront the raw data. And let me tell you, raw enterprise data is a nightmare. Information gets pulled from core banking, servicing platforms, and collection systems that were literally never designed to talk to each other. We are talking about 37 different spellings of just 7 canonical status codes. The concept of a loan being current might show up as current, cur, good standing, or current in all caps. You've got date formats clashing between ISO standards, American formats, and text abbreviations. You have Boolean yes-no flags represented as y/n, 1/0, or true-false. You even run into logical impossibilities, like 23 loans showing a negative principal amount, or records where the text status says current but the days past due flag says the borrower is 45 days late. It's a mess.
Section 2. The 3-tier engine, a semantic solution. To solve this absolute chaos, Sumit's project introduces a profoundly elegant engineering solution, a semantic engine. And really notice that word, semantic. It doesn't just calculate some canonical number, it actually translates meaning across the entire organization. It establishes a strictly governed framework where the data is meticulously cleaned, a single source of truth is established, and yet, and this is key, the legacy definitions of the risk, finance, and board teams are perfectly preserved and explained. The engine pulls this off through a strict 3-tier architecture. Tier 1 is that messy raw data we just talked about. Tier 2 is the conformed data pipeline, which normalizes that mess. And Tier 3 consists of metric-ready inputs. The absolutely crucial point here is that these tiers are strictly separated. Raw data transforms into conformed data through a pipeline that is item-potent. That's a fancy way of saying you can run it 10 times on the exact same input and get the exact same perfectly auditable output every single time. That middle tier, the conforming step, relies on 9 very strict, heavily documented business rules to clean the data. Remember that contradiction I mentioned where the system says a loan is current but also 45 days past due? Well, how do you handle that? The conforming rule explicitly states that the numeric days past due value is trusted over a lagging categorical status text. It just makes logical sense. Another rule states that if a loan's charge-off flag is set to true in any system, it forcibly overrides whatever the text status field says. These 9 rules act like a filter, systematically collapsing all that enterprise chaos into reliable order.
Through this rigorous conforming process, out of 2,013 raw, messy loans, exactly 1,953 successfully pass the validation steps. Now, notice what happens next, because it's brilliant. These 1,953 loans become frozen, immutable Python objects. This is a massive defensive programming choice. By making them immutable, it becomes structurally impossible for one team's calculation to accidentally mutate the data and corrupt another team's calculation downstream. The data is locked in.
Section 3. Reconciling gaps, explaining the difference. Once the data is conformed and locked in, the engine doesn't just calculate one official number and go tell everyone else they're wrong. That never works in corporate politics, right? Instead, it generates a canonical rate and then programmatically explains the exact specific divergence of every single legacy variant. It acts as a reconciliation engine, translating those confusing gaps into plain language. But before we look at the exact numbers, let's establish our unit of measurement. We are going to be talking in basis points. A basis point is simply 1/100th of 1%. So 100 basis points equals exactly 1 percentage point. This is the standard unit of precision in finance simply because percentage points are way too coarse when you're talking about millions of dollars in loan exposure. Every basis point matters. So the engine establishes the canonical baseline default rate at 22.14%. And this isn't just some arbitrary number they picked out of thin air. It's formally defined in a specification document before any code is even written, aligning tightly with international credit risk frameworks like Basel III and IFRS 9. It uses a 90-day past due threshold and measures gross exposure, meaning it includes the principal plus accrued interest without deducting recoveries. This canonical rate serves as the ultimate formal benchmark against which all those other legacy metrics are measured.
And this brilliantly illustrates the power of the reconciliation engine. Remember the board's terrifying 72% default rate? The engine doesn't just say, hey, the board is 4,955 basis points higher than the baseline. It automatically generates a narrative explaining exactly why. It attributes that massive 4,955 basis point gap specifically to the board's conservative rule that categorizes 957 performing restructured loans as defaulted, whereas the canonical rule considers them performing. It even pulls specific exemplar loans to prove it. Instantly, a heated, stressful boardroom argument turns into an auditable, completely understandable fact.
Section 4. Hunting silent bugs, adversarial testing.
This brings us to what I like to call the dark matter of engineering. Most developers test the happy path, just making sure the code works when the data is clean and normal. But this project introduces the discipline of adversarial testing. Built directly into this engine are exactly 142 adversarial tests. These aren't tests to prove the software works, they specifically exist to prove where it might fail. In financial systems, a loud bug that crashes the software is honestly fine because you see it and you fix it immediately. A silent bug, though, one that outputs a totally reasonable-looking but mathematically incorrect number, that can corrupt capital allocation decisions for years without anyone noticing. These 142 tests exist solely to hunt those silent bugs. The system utilizes 3 specific adversarial modes. First is boundary testing. Instead of testing a loan at, say, 50 days past due and 100 days past due, the engine tests the exact threshold, 89, 90, and 91 days. Off by 1 errors at thresholds are notorious in finance, so you have to lock them down. Second is fuzz testing, which throws thousands of randomized portfolios at the engine to ensure mathematical invariance hold, like ensuring the default rate never, ever drops below 0 or exceeds 100%, even if you feed it a completely empty portfolio. And third is scenario testing, which means deliberately feeding the engine pathological contradictions, like a loan that is simultaneously flagged as restructured and charged off, just to see how the logic handles the collision.
And this adversarial approach isn't just theoretical, it has real stakes. During development, the scenario test I just mentioned, a loan that is both restructured and charged off, actually caught a massive silent bug. The code was applying the restructured exception without checking the charge-off flag first. Catching that logical error resulted in a 127 basis point correction to the canonical rate. To put that into perspective, in the real world, that silent bug would have meant $655,000 in defaulted exposure was misclassified and completely hidden from the reporting. adversarial testing literally prevented that from happening.
Now, there is a highly technical choice at play here that makes absolutely all the difference when dealing with financial data. Most programming languages use binary float arithmetic for fractional numbers. It's super fast, but it's an approximation. In standard float arithmetic, 0.1 plus 0.2 doesn't actually equal 0.3. It equals 0.300000000000004. Now, across 1,953 loans, these tiny invisible rounding errors accumulate non-deterministically. To solve this, the engine completely abandons float and uses Python's decimal type instead. Yes, it is computationally slower, but it is mathematically exact. It ensures absolute, reproducible precision down to the last penny.
This profound domain expertise did not go unnoticed. The S4 Data Analytics Hackathon judges specifically cited this in their Honorable Mention Award. They praised the project for demonstrating, and I quote, "a discipline that reflects genuine understanding of floating point error in financial systems, not just coverage for its own sake." It signaled that the engineer wasn't just checking boxes to get the code to run, but deeply, truly understood how code behaves at scale when real money's on the line.
Section 5. Governing Metrics, a Strategic Blueprint.
So we have this incredibly robust, battle-tested engine. But how does it actually live inside a company? Well, it's deployed operationally as a governance framework for the entire organization, ensuring that the reconciliation process is accessible to every downstream system. The calculation engine is exposed as a REST API. This means dashboards, BI tools, and internal services can query it seamlessly. And crucially, every response from this API is self-documenting. If a downstream dashboard pulls the 22.14% rate, it also receives all the metadata detailing exactly how that number was calculated, the definition version, the observation date, the specific thresholds used. The number is never orphaned from its context. Furthermore, all inputs are strictly validated by Pydantic, ensuring that garbage inputs are outright rejected before they can ever trigger a calculation.
This entire system is held together by world-class engineering principles. The team adopted a document-first approach, writing out the metric definition before typing a single line of code. They utilized version definitions so historical numbers always remain perfectly reproducible. And importantly, they relied heavily on architecture decision records, or ADRs. If you aren't familiar, these are short documents capturing exactly why a design choice was made, like why was 90 days chosen for the canonical baseline instead of 60. Keeping these records permanently prevents the accumulation of legacy debt and stops that classic developer question of why on earth did we build it this way 6 months down the line? What you should really take away from all this is that this framework isn't just for fintech loan portfolios. Not at all. This semantic engine is the ultimate blueprint for literally any contested metric in your organization. Think about revenue. Sales, finance, operations, and customer success all recognize revenue at slightly different times. Or headcount. HR counts full-time employees, finance counts full-time equivalents, operations counts desk seats. This architecture, having a canonical definition with preserved legacy variants and an explainable reconciliation engine, can solve the chaos for absolutely any contested enterprise data. Which leaves us with a pretty critical question to consider about your own workplace. Think about your most important metrics right now, the ones reported to the board, the ones that actually drive your strategy. What is your organization's default rate? And who exactly is calculating it? Are you operating with a semantic engine that reconciles the truth? Or are you just arguing over words in a boardroom? Thank you so much for joining me on this explainer. Until next time, stay focused and keep learning.